The first speaker of today is Gabriel Paternain from Cambridge, and he will talk about symplectic topology of Monier's critical values.
Okay. Thank you very much. I'd like to thank the organizers for this wonderful opportunity to be here today. I mean, this meeting is just as pleasant and friendly and as good as the one 2 years ago. Now, I feel a little bit like in some sort of press conference with all these cameras, so I'll try to not to move too much and try to ignore them if I can. Okay, so what I like to talk about, sort of more or less started sort of 2 years ago, just about the time of this very same conference. We sort of met in Kyoto with Kai and Urs, and then by then they have sort of just finished doing the new Floer homology for the Rabinovitz action functional that we heard about in some of the previous lectures, and we are going to hear also in some of the subsequent lectures. And after sort of talking for quite a while, we sort of did realize that a lot of the things that they've been doing kind of have a very, very similar flavor with some of the things that actually Gonzalo talked about, that we did some years ago, trying to prove the Palais-May condition and bounding this time that was going to infinity for the free time action functional, and realizing that you could do that for values above the Manier critical values. So the whole thing seemed to have remarkable similarities. So we basically spent several days in which they told me what they were doing, and I didn't understand much, of course, and I was trying to tell them what we have done before. So this is more or less what came out of that, and so I'd like to sort of tell you a little bit about that. So I'd like to begin by telling you briefly about the Manier critical value that was already sort of introduced, but I will do it in a slightly more general setting. I will discuss the exact case, which was also mentioned yesterday. I'll talk briefly about some of the symplectic properties, comment on sort of Rabinovitz Floer homology, and then tell you about what we think the global picture ought to look like, and then what we can actually prove, and then tell you about various sort of open questions about that. Okay, so let me sort of begin by telling what the setting is. So I have a closed Riemannian manifold. I have some potential, some function u, and then I have, this is sort of a very important feature, I have this sort of closed two-form sigma, which you can think as a magnetic field, given. So I have sort of three objects, and as a matter of fact, you can think about zero potential, if you like. I mean, the really interesting stuff takes place just with the metric and the two-form sigma. Right, okay, so you have the canonical projection from the cotangent bundle into M, and you can twist the usual symplectic form PDQ by adding the pullback of this closed two-form on the base. So you sort of pull it up, you add it to the standard symplectic form, and this gives you a new symplectic form called the twisted symplectic form. So we get a sort of new symplectic manifold, if you like, which is T star M with this form, twisted form omega. Okay, and then I look at the physical Hamiltonian. The Hamiltonian is usual kinetic energy plus a potential. And this is the key assumption that I'm going to make. And I'm going to assume that the two-form sigma vanishes on pi 2, or if you like, what is exactly the same thing, when you pull the two-form sigma to the universal covering, it becomes exact there. Okay, so this is sometimes called the weakly exact case. Okay, so I don't think really we have much to say when sigma doesn't have that property. We haven't even looked at that, even thought about that, because this case was already kept us very busy for quite a while. Okay, so, but you see, this is important. The form sigma can be non-exact on the base. It could be a sort of genuine monopole. I like to sort of call that the monopole case when the two form is non-exact on the base, but it could become exact on the universal covering. Okay, so what is the Manier critical value in this context? Well, you do a sort of minimax thing, as I sort of indicated there. So basically, you first you lift everything to the universal covering, so you basically unfold the primitive, And then you look at the Hamiltonian H that I had before, lifted, so it's the lifted Riemannian metric and lifted potential. And you basically evaluate that Hamiltonian on the value of the primitive at the point Q. Yeah? And then you do the sup over all Q in the universal covering, and then you do the inf over all possible primitives, yeah, of your symplectic form. So that gives you some real number, and if you like, in an explicit form, if you want to write out the formula for H, this is what you get. Usually, as I said before, I might not even think about the potential, so you might want to think that the Magnete critical value is doing that sort of minimax for the primitives. Yeah? Okay, now one thing that you notice right away from the definition, yeah, so the first thing you might want to ask yourself is, I mean, this doesn't have to be a finite thing. In fact, we will see in a minute that there are many interesting cases in which this is not finite. Yeah? So, but what you do see right away is that this becomes finite if and only if there is a bounded primitive. Yeah? So namely, there is a bounded primitive, so there is a primitive for which that sort of remains a finite number. It is important that you do that with respect to the lifted Riemannian metric. Yeah? So the fact of being bounded on the universal covering is not dependent on the Riemannian metric you choose. If you have two Riemannian metrics on the base, yeah, if it is bounded with respect to one, it will be bounded with respect to the others, because the two differ by a sort of uniform Lipschitz constant. Yeah? So it's really a sort of intrinsic property, if you like, of the cohomology class of the two form. Okay, very good. Now, so here's one sort of big class in which this critical value is infinite. So if your fundamental group is amenable, I don't want to define what that is, because I mean, I can sort of tell you briefly, you can average things when you have a group that is amenable, but I can give you examples of what things are actually amenable. So if you have something that is abelian or nilpotent or solvable, yeah, that is amenable. But if you have something like the fundamental group of a manifold of negative curvature, that is really very non-amenable. Okay, so this is the way you should probably think about that. So fundamental groups of surfaces of higher genus are non-amenable, but the fundamental group of the torus is of course amenable. Okay, so as soon as you have a pi 1 which is amenable, it's not difficult to see, and you're in the monopole case, in the non-exact case, that the Magnete critical value becomes infinite. Okay, so this is basically because if you were to have a bounded primitive and you had a pi 1 which is amenable, you would be able to average and produce a primitive for the form on the base, which you can't if you're assuming that it's not exact. That's really morally what's going on. Okay? Right, so what do we want to do? Well, we want to do the following thing. We would like to understand, now you look at the energy levels of this Hamiltonian, and you would like to understand how these energy levels change as you go through the Magnete critical value. Okay? This critical value may be infinite, but in many cases it will be finite, and you would like to understand what kind of phase transitions you have. We've known that there are quite a long time that there are sort of drastic changes at the Magnete critical value, but we'd like now to get our hands on symplectic topological properties, especially in this setting. Yeah? Okay, so the properties that I would like to discuss are, I think, for many people in this audience, quite familiar. So I'd like to sort of talk a little bit about existence of closed orbits, about whether we can displace sets by Hamiltonian diffeomorphisms. I will sort of briefly remind you about these definitions, run through them quickly. Whether these hypersurfaces are contact type or whether they are stable. I will come back to the definition of that. This is sort of one of the features, if you like. Okay, now the study of the systems of this sort of twisted cotangent bundles with the Riemannian metric, I think it's sort of fair to say that it was initiated sort of in the 60s by Arnold and Novikov. Novikov has a paper in the sort of early 80s in which he tries to do Morse theory for a function and closely related to the function that actually Gonzalo was talking about. And there's been, enormous amount of activity, if you like, this class of systems. In some sense, it's a very good sort of prototype to see how much you can do with the tools of symplectic topology, right? I mean, the fact that we haven't yet able to understand the whole thing, or whether we always have closed orbits and when and how, is a sort of indication that they are sort of tough nut to crack somehow, yeah? There's a lot of good things that one can say, and it's a very good playground to see how far we have advanced with symplectic topology, if you like. Okay, so Right, okay, so let me begin with some sort of basic examples. I'm sure some of you are actually familiar with this, but sort of quickly too. So the first basic example is an example that you do in, if you look at sort of high school physics, if you like. So you take the flat torus with the uniform magnetic field, they form dq1 wedge dq2. In that case, you can sort of solve everything. The orbits are all closed, yeah, and they have a radius that is related to the energy of the hypersurface by the square root of 2k. So the larger the energy, the larger the larger the circles. Yeah, so you might think that in the case of infinite energy, you hit the geodesic flow of the flat metric. Yeah, and for very, very low energies, the circles become very, very small. So in that case, the Magne critical value is infinite. There's no bounded primitives. You cannot find a bounded primitive for dq1, dq2. So the obvious thing, q1, dq2 is not bounded in R2, and there's no way of finding a bounded primitive. So in that case, the Magne critical value is infinite, and at infinity you are sitting exactly with infinite energy, you get the geodesic flow. Now here, all the energy levels have, since all the orbits are closed, they have contractible closed orbits. Yeah, they're actually not contractible in the energy level, because there's some little accident with T2, but they are actually contractible in the whole tangent bundle or in the torus itself. Okay, now the other sort of famous example is the uniform case, again, of a closed hyperbolic surface with the area form. So if you just have your favorite Riemann surface, and you take sigma as the area form, dx wedge dy over y squared in the model of the upper half plane, then things there are different. Yeah, of course, there is a primitive. The primitive is, let's say, dx over dy, but that primitive is actually bounded with respect to the hyperbolic metric. Sort of simple exercise. Yeah, because, and in that case, with a little bit more work, which I don't want to get into, it's not easy, it's not difficult to check that in that case, the Magne critical value exactly happens at the value 1/2. Okay, now how is the dynamics? Well, the dynamics is also very easy to sort of describe. I mean, this is a homogeneous example, right? The underlying group is PSL2R. So all these flows on the energy levels are just actions of one parameter subgroups. So you can sort of say everything you want to say. Yeah? And it's very easy to check that if you're above the Magne critical value, then everything is an also. So you in the sort of picture of the Lie algebra, if you like, the Lie algebra of PSL2R, what you have really is you have this sort of cone given by the Casimir, and what is happening is that you basically go through this. As you sort of change energy, you sort of get into the hyperbolic elements in the Lie algebra into the elliptic elements, basically, as you sort of change the energy. And there's some phase transition there that takes exactly at the place of 1/2, and that's the horocycle. Yeah? You can also even picture this, if you think about the Poincaré disk, the geodesics are circles that meet the boundary at a right angle, then you switch on your magnetic field, and then you sort of start bending these things, and then the orbits there are also pieces of circle, but they meet the boundary at an angle, and as you sort of turn off the magnetic field, at some point those circles become actually tangent to the boundary. That's when you hit the horocycle flow. Once you pass that, then the circles become actually real circles. The full thing is contained in the disk, and then your flow corresponds to the flow of a one-parameter subgroup, which is elliptic in the Lie algebra PSL2R. And then we are now with a situation in which we have all closed orbits, all orbits are actually closed, and they are contractible. And in fact, the levels above the energy 1/2 are contact, and the levels below 1/2 are also of contact type. And at the horocycle, of course, is not contact; it's very unstable, and we have no closed orbits. Yeah, it's in fact uniquely ergodic. The only invariant measure is just the volume. Yeah. Okay. So these are the two sort of basic examples. All right. Now there is a sort of special case, and I want to sort of briefly discuss this to relate to what Gonzalo mentioned. Now, what happens if the form is exact? So maybe I'd like to have a little picture here that I will be sort of feeling as we move along. So basically, So in the exact case, and in the non-exact case, and this I will plot the energies, the various energy values. So if we have a form which is a two-form which is exact, we can sort of play the same game and do the same minimax principle, but now running over primitives on the base. Yeah, now primitives on the base. Okay, and then you get another critical value. Okay, so that's the same critical value that was mentioned in the first talk by Aguantandolo. Yeah, that's what Magnier called the strict critical value. We call that C naught. Strict critical value here. And the way to think about this is that if this is non-exact, you want to think that this strict critical value does exist, but it's actually infinite. Yeah? So I want to think that there is a sort of C naught there, which is infinite. Okay. Now this is the value that actually connects with open matter theory proper somehow. So this is exactly, can also be characterized as the minimum of Mather's alpha function, or if you like, as the, if you do sort of Mather's action minimizing principle, you integrate the Lagrangian, and you do that over all measures with zero homology, you get some value and you sort of change the sign of that basically, and you get that C naught. So all the minimizing measures in open matter theory, they live basically here. Yeah? So this is the realm, if you like, of open matter. So this is what I just say. So this, we get the minimizing measures with zero homology in that sort of value C naught. Okay, now the value of C naught, alpha, and the various invariant sets that sort of pop up in open matter theory, like the Magnier set and the Aubry set and so on, those have been characterized in terms of symplectic topology, if you like. There are sort of versions that they tell you that these values are in some sense invariant under symplectomorphisms, even though in principle they seem to be defined using, like in this case, the Magnier critical value, using Lagrangian graphs, that they seem to sort of be dependent on the vertical structure of the cotangent bundle, if you like. But in fact, they are not. This can be seen. So there's actually also a paper by Viterbo on symplectic homogenization, which is sort of also some of these things are captured from a symplectic topology point of view. So there are, I mean, precedents of what I am saying. I mean, this is not something that just happened in the last couple of years. There were some sort of previous things sort of indicating very strongly that these things had a strong sort of symplectic topology flavor. Okay, so, but now there could be a gap, yeah? So you see so it is obvious that this C naught is greater than or equal than C, yeah? It's obvious from the definitions. But in principle, there's no reason why these two things cannot be distinct. And in fact, they are. So, more than 10 years ago, I sort of discovered with my brother Miguel that this actually could happen. So could capture the first little example showing that these two things could actually separate. Yeah? So in principle, the picture in the exact case could look something like this, with this other sort of Magnier critical value. This is what actually Gonzalo was talking about yesterday, what he called the universal value, the critical value of the universal covering. Yeah? He called it CU. I'm just calling it C here. Now, the thing is that this is actually, the gap is very prevalent. So in some sense, so I like to think that in the monopole case, the whole thing is a gap. Yeah? So the C will be here eventually. I mean, C could be infinite, but in the case if you have a bounded primitive, anything above C, the way you have to think about that is this is the gap. Yeah? In the monopole case. If it is exact, then you still have the gap, and as a matter of fact, in some sense, most manifolds will have the gap. So here is one example. It's not the example that we came up with Miguel, but the example that we did with Kai and Urs, which I think is even more sort of convincing than the sort of example that I had with Miguel. In some sense, it's sort of the best example we have to sort of illustrate this. So you have a gap of size actually 1/4 that appears in the PSL 2R geometry. Yeah? So now I take PSL2R as a sort of 3 manifold that will have a lattice, yeah, and mod out by a lattice. Yes? And I get that is my 3 manifold. It's some sort of circle bundle. It is the unit tangent bundle of a surface of higher genus, yeah? But then I put my system on that. So in some sense, the example of the whole cycle flow is a symplectic reduction of this one, yeah, basically. So as a form sigma, in this case exact, you take the form sort of dx over y plus d theta, yeah? So you might wonder why you add d theta if you take d, that is going to be 0. Yeah, true. But the thing is that if you know that, if you don't add the d theta, then what you get inside is not left invariant. But if you write it like that, dx over y plus d theta, that one is left invariant. Yeah? That is the sort of one form. Geometrically, that is the same thing as the sort of connection one form that you get in the unit tangent bundle of a surface when you take on the base the area form. Yeah? That's exactly the same thing. So in that case, I cannot show you, I mean, that would take a sort of bit of work, but in that case, it's not difficult to see that you get a size of exactly a gap of exactly size 1/4. So in fact, this is a sort of interesting energy level. Yeah? So Paternain has studied, I only learned this from Leo later, that he told me that he had looked at this example at the various integrability properties at the Magne critical value. Right? This sort of integrable in the non-commutative sense, but not integrable in the usual sense. It's quite peculiar example. Okay, but now to sort of complete this this discussion, there is a sort of previous result by Fatih and Ezequiel Maderna that show that if pi1 is amenable, then there is no gap, basically. Yeah? So basically, I mean, if you sort of work on manifolds like the torus, in the exact case, you won't see the gap. Yeah, but if you sort of go into things that are sort of negatively curve flavored, then the gap will immediately appear. Okay, right, this is what I just said. Okay, now what are the symplectic properties that I like to talk about? Well, some of them I have sort of mentioned. Yes?
Sorry, Gabriel, you said that typically you would expect a gap. Do you know that this is the case?
Well, yes, we have some theorem about that, saying that if you begin basically with a sort of, suppose you have an arbitrary manifold with a 2 form with a bounded primitive, and you take the unit circle, and the primitive is an integral, the 2 form is an integral 2 form, and you take the unit circle bundle over that with a sort of appropriate Euler class, then you will see a gap there, just like in the PSL2R in general. So that will give you sort of, you know, as many manifolds as you can probably dream of with a gap. What was it? Yes, okay, so this placeability. So this is, I mean, I'm sure you know all this, but this is just to sort of remind you. So you said that a set is displaceable if you have a Hamiltonian diffeomorphism compactly supported and move it away from itself. Yeah, so that's a sort of one property that I'll be discussing, and this is relevant for our discussion if we, let's say, start looking about closed orbits, because of the following result by Schlenk that says that if you can displace an energy shell, if you like, everything underneath with energy less than or equal to k naught, then you can show in this setting, in this setting of twisted tangent bundles, that the hypersurface, almost everywhere, the hypersurface will carry a closed contractible orbit. Yes. So this is one reason why you would like to displace, because if you can displace, then you will be proving existence, at least almost everywhere existence of closed orbits. I mean, not just for the system, but in that case for any sort of hypersurface in there, and not just a hypersurface given by kinetic energy, let's say. Okay, so let me remind you about what contact type is. So contact type is when you restrict your symplectic form to the hypersurface, then that becomes exact, and you can choose a primitive for that is actually a contact one form in sigma k. So contact meaning that if you do a lambda wedge d lambda to the n minus 1, where n is the dimension of the base, then that becomes a contact. It's a volume form. Okay, now here we have a sort of new thing somehow. So we call this virtually contact case, so because that actually happens, and happens again rather frequently. So what is virtually contact type? Well, you want to have the same thing as contact, but on the universal covering. And you want some uniformity on the universal covering. So you say that the hypersurface is of contact type if, when you go to the universal covering of the hypersurface, it becomes of contact type there, but with uniform bounds. With uniform bounds means that the form that you get there is actually bounded in the C0 norm, and when you do that form over any lift of a vector field which is tangent to the characteristic foliation, that form is actually positive and bounded away from 0 by a uniform amount. Yeah? So we call that a virtually contact case. So why is this important? Well, because basically what I will try to convince you is that if you are here, basically these are all virtually contact. And the same here, yeah? So this will be virtually contact. But in general, they may not be contact, and they may not even be stable. Yeah, that would be a bit of a surprise. Okay, now what is stable then? When stable is this sort of notion that it's an enhancement of the contact type property. Yeah? So basically, Kai asked me this great question in Tokyo, right? I mean, so Kai asked me, what do you know about stable magnetic flows? This was his question. So, okay. So what is stable? So stable is now, no, you have, stable is, this is the formal definition, so the hypersurface is stable if there is a one form such that it's non-zero in the characteristic foliation, but the characteristic foliation annihilates the kernel of, annihilates d lambda. Okay, right. Now, there are many ways of looking at this property. So basically, you're decoupling, right, the contact condition and sort of retaining something. Yeah, so like the sort of minimal thing. So you want at least to have a form that will allow you to define some kind of red vector field. Yeah. So if you have a form like that, then you can define in a sort of canonical way a red vector field, which would be a vector field with the property that lambda is actually 1 on the vector field, and the vector field annihilates d lambda when you contract it. But now there are other ways of looking at this property. Well, okay, sorry, before I go into that. So obviously if you have something contact, it is stable, yeah? But the thing about this notion is that for a hypersurface to be stable, you don't even need it to be the form omega to be exact, yeah? And this is actually, very good for us, because if you want to understand cases like this, there's no hope that the symplectic form is going to be exact, yeah? Except again in some accidents in dimension 2, but other than that, the form will not be exact, the twisted symplectic form. So you have changed the cohomology class of the symplectic form. So it doesn't make sense anymore to ask about whether they are contact. So then you ask whether they are stable, yeah? So why is that? Okay, well, okay, so first, I'm getting ahead of myself. So let me just sort of give you one example of a stable thing which can never be contact. So we go back to the very basic high school example of physics, yeah? So the two torus with the area form. So the form is sort of dq1, dq2. And of course, in the case of a two torus, if you lift it to the energy hypersurface, to the three torus, it's not exact. So there's no way you can sort of say that's going to be contact. Yeah? But it is stable. And the stabilized in one form is actually quite to describe in geometric terms. So if you write the unit sphere bundle as sort of, the base cross the fiber, it's a sort of trivial bundle, then the stabilizing form comes exactly from the angular form on S1. And in that case, it's actually closed. And that's no surprise, because in this case, the magnetic flow is a suspension. So basically, the stabilizing one form is the one form that, if you have a flow that is a suspension, there's always a sort of closed one form that is non-zero on the vector field. Okay, so that is an example in which you have something stable, which is not cannot be contact even for obvious reasons. Okay, now, why this sort of condition? Well, you can be interested in this condition for various things. One thing, I think this is probably the underlying reason why Kai and Uns have been interested in this, is because once you have this condition, you can prove compactness results in symplectic topology. So there's a sort of, in symplectic field theory, this sort of work by Bourgeois, Eliashper, Giventhal, Hofrans, Vysotsky, and Sender. So I'm not like Sir Gonzalo. So he had 4 names, and I have to remember 5 this time. Yeah. So okay. They basically prove prove compactness of the moduli space of pseudo-holomorphic curves, but if you have the stable condition. Right, now why the name stable? Well, stable is because the notion was actually introduced not in this form, but quite early, sort of in the 90s by Hoffer and Sender, in the following form. So this is, having such a one form is the same thing as saying that your hypersurface has some thickening, namely some sort of neighborhood, right? In which the characteristic foliations on the sort of nearby surfaces, yeah, by a thickening I mean something of the form hypersurface cross minus epsilon epsilon, yeah? And each one of those hypersurfaces has a characteristic foliation that is actually smoothly conjugate to the characteristic foliation of the hypersurface that you started with. So the reason why they were looking at this is because if you have, sort of results on almost everywhere existence of closed orbits, with the stability condition, you will be able to prove existence of closed orbits exactly at the energy level. Yeah, that's basically the reason. Now, it turned out that this way of looking at it is the same as the definition that I've given you before with the one form, which also turns out to be the same thing as something that Sullivan looked at in the 70s when he asked this sort of general question. You can ask the sort of following general question. If you have a vector field on a manifold, let's say a vector field without singularities, when it is geodesical, namely, that means is there a Riemannian metric such that that vector field, the orbits of the vector field are the geodesic of that given Riemannian metric. And that turns out to be exactly the same thing as the stability condition in this case. And then Sullivan gave a criteria in terms of foliation cycles, which is sort of, very elegant, but in some way kind of useless and cannot really be useful for much. But okay, Rabinowitz action function and Rabinowitz flow homology. So this was explained in the first lecture by Dandolo, and it will be discussed again, I guess, in Ur's lecture. So here I'm just going to limit myself to sort of briefly remind about the functional mumble, a couple of words about the Lagrange multiplier, and then tell you what's the significance of that homology here, and when it can be defined, and under what conditions, and so on. Yeah? Okay, but let me just remind about this sort of functional. So basically, you have a sort of pair of things now. You have a loop which is contractible on the tangent bundle, and you have some parameter eta that you want to think as a Lagrange multiplier, and that is the functional that has a sort of wonderful property of having the critical points, which are not just, but having the critical points exactly on the energy level h equal to k. Yeah, this was explained by in the lecture yesterday in the morning. Okay. Right, now the key for sort of constructing these homologies, yeah, is to get a C0 bound on the Lagrange multiplier. So this is really, so you have to do some kind of an infinity estimate for the Lagrange multiplier. And this is kind of a problem which is very similar in spirit to the problem that actually Gonzalo was talking about yesterday when he was saying that the times could go off to infinity. Yeah, basically, you want that not to happen. Okay? So if you can bound the Lagrange multiplier, you are usually in very good business and you can define this homology. Now, this cannot be achieved for any hypersurface, yeah? Unfortunately, you can, because if you could, then you would be deriving sort of conclusions which in some sense false. But the point that we are sort of, one of the things I'm trying to say to this is that you can actually do that if you have either the stable condition or the virtually contact condition. Yeah? So if you have stability and the virtually contact, then you can define that. And there is another sort of condition coming up in a second. But so first, as was mentioned yesterday, Chiribak and Frauenfelder actually constructed this Rabinowitz flow homology in the contact case, actually restricted contact case, to be technically precise, about 2 years ago, and the paper has now appeared in Pacific Journal. Right. Now, the additional technical condition that one needs in the stable case is a sort of coercive sort of property. You need to have some kind of relation between period and action, without which there's nothing we can do, basically, because we cannot get compactness on C0 compactness on the loop, not on the Lagrange multiplier, but on the loop, really. That's what we need, this Taymi's condition. The Taymi's condition essentially says that, so you can read the sort of left-hand side as as the period of the orbits of your red vector field, and the right-hand side as the symplectic area of the closed contractible curve. So you want to sort of say that if you have period action inequality in that sense. So basically the way this is used is that if you have some sort of, if you know that your symplectic area is between some bounds, then you have some control on the periods of closed orbits. Okay, and then the theorem, having sort of defined all this, kind of looks like this in general. So you have a geometrically bounded symplectic manifold, now with a symplectic form that vanishes on pi 2, like the examples that we've been discussing. Right, so then in that case, the claim is that you can define Rabinovitz Floer homology for a tame stable hypersurface, and it has a property of being invariant on the same stable homotopy. So namely, if you sort of move your hypersurface with a family of smoothly varying stabilizing one forms, and you do that along tame hypersurfaces in which the constant A that I had before doesn't change, yeah, then the homology remains unchanged. This is the sort of main virtue of all these homologies, right? They are invariant under deformations. Right. Now, we can do the same for the virtually contact hypersurface. Again, you need here a sort of mild technical thing about the fundamental group of the hypersurface injecting in the fundamental group of the ambient manifold, or you can assume also some kind of restricted virtually contact type property. But in the cases that we have in mind, in dimension greater or equal to 3, basically that condition in the virtually contact case comes for free. So. Right, and then the other sort of very good feature of this homology is that if you can displace, then it vanishes. Yeah, this is a wonderful thing about this homology. So if you have a hypersurface and you can displace it by a Hamiltonian diffeomorphism, then that thing has to vanish. Yeah, it's a sort of yes.
Can you go back and show the tameness condition?
Yes. Yeah. So the left-hand side, so if you like, is basically the period of the associated red vector field, and the right-hand side is the symplectic area. I'm sorry? Tame, I will give you, yes, yes. So, but by having asked that, it means that the end of the lecture may overrun over 5 minutes or something. So, yes, I'll try. We have plenty of examples of that, yes. So, in fact, there will be quite a. So, yeah, I'll come back to that. But if you want to think about one of those, the PSL2R is tame, or below the Magnier critical value. Okay, so, right, the other very good thing is that if the Rabinovitz Floer homology vanishes, then you have a closed contractible orbit. Yeah? So basically, this kind of recovers what Schlenk proved using capacities in a way, if you like, right? That if you can displace, then you get a closed contractible orbit. Yeah? But you could say that in some sense, these homologies are detecting that. Okay, so Urs might talk about what goes into the proof of this later on, I guess, tomorrow. So I like to think the organizers for the timing of the lecture, right? The timing of the lecture that yesterday was actually Gonzalo and Dolo, and then that sort of introduced the topic, and then I can safely hand it over to Urs tomorrow for the technical details. Okay. So the extension to the virtually contact case is really not. It's not a big deal. The big deal is that it's actually useful. Yeah, so we can actually use it. This is it. Yeah. So basically, it's the same sort of idea that Kai and Urs had in the paper in the contact case. Now, the extension to the table case is not a minor business. This is technically heavily involved. And there are many reasons for that. You have to choose your Hamiltonians that define the hypersurface in a very sort of careful way. But one of the sort of main hurdles of this is one sort of big difference is that the stability is more general than the contact condition, but it's not open. Yeah? So the contact condition, if you have a hypersurface that is of contact type, it's sort of not difficult to see that if you move to a nearby hypersurface, then it becomes, that is also contact. And this is very important because when you're trying to define all these homologies, you want to begin with a situation in which your dynamics have all the closed orbits in more spot in some sense, or non-degenerate. Yeah? Okay. So then the way this is usually done in the contact case is you say, well, if I have something that is not more spot, I can perturb it to a nearby situation in which all the closed orbits are actually non-degenerate, and then I carry on my business there, and then I prove that it's invariant deformation and so on. Now in the stable case, you cannot do that. You cannot do that. And one of the questions that we had a couple of years ago, whether this thing was actually open or not, that we didn't know, it wasn't known. And now we have an example that showing that this is in fact not open. The example is actually quite a sort of cute little object. It's basically the geodesic flow hyperbolic 3 manifold on the unitangent bundle that happened, but which can be seen somehow as that the geodesic flow there has a very special feature, is that the space of invariant two forms is actually two-dimensional. So there is a Hamiltonian structure there, which is actually not the usual symplectic form, but something else, and it's stabilized by the usual symplectic form. And the moment you sort of perturb, it becomes non-stable. This is really curious, right? Because I mean, the geodesic flow hyperbolic manifold is an osov. So you're going to think, well, if I perturb something, an osov, of course, remains an osov. But the thing is that the thing nearby will be Z0 conjugate. Yeah? And what we are exploiting here is that these are not C1 or C2 conjugate. Yeah? So then you won't be able to find a form lambda of class C1, let's say. Yeah? So it's a sort of, what's involved in this example is a sort of subtle thing between the smoothness of the stable and unstable bundles, basically. You begin with something very smooth, and then you perturb, and genetically that's not smooth. So then it's not geodesical. Okay. Right, so then what is the sort of picture that we have? So maybe I should sort of speed up a little bit. So some of these things I have already said. So basically, if you are in the supercritical case, you would expect this to be virtually contact, and it may or may not be stable. Now, I will convince you about that in a minute with another theorem, that it's not stable. Now, you expect the Rabinowitz flow homology here, since it is virtually contact, to be defined. It is defined, that's actually true. But what you would like to prove is that it's actually non-zero. Yeah? So you want to prove that it's non-zero to sort of be able to claim that anything above here is non-displaceable. Yeah? So basically you want to sort of say that anything above here is non-displaceable with non-zero Rabinowitz flow homology. And you sort of expect the dynamics there to be geodesic flow-like with closed orbits in every non-trivial free homotopy class. That's what you would expect. What do you expect at the Manier critical value? Very unstable, yeah? That means, okay. So, except there's again some accident here with the two torus in which there are sort of examples showing that in fact it can be contact even. But if you're away from the two torus, you would expect the Manier critical value to be very unstable. And then for subcritical energies, this is where, nothing that I'm going to say, there are counterexamples to this, but I'm less convinced I want to be able to prove everything that I'm going to say, but we have to have some kind of a sort of, general view on this. But one expects this to be may or may not be of contact type. We have actually examples of both things here, below the Manier critical value. You would expect it to be stable and displaceable, at least when the Euler characteristic is zero. So if there's some sort of obvious reason for not being able to displace, and this is sort of having non-zero Euler characteristic. But if you have zero Euler characteristic, you will be able to, you expect to be able to displace. Then, if that's the case, then you would have RFH defined, and you will get a contractible closed orbit below the Manier critical level. so this is what one sort of expects. Okay, so what can we actually prove then? Okay, so this was our sort of first result. So the Rabinowitz flow homology is always defined whenever you're above the Magnier critical value, which are always virtually contact. Okay, so this is well known. And the sort of invariance of the homology allows you to prove rather easily that if you have some background metric of negative curvature, then the Rabinowitz flow homology is non-zero. The reason for that is because if you have some background metric of negative curvature and you have this twisted symplectic form, then for the you put the twist and you go to very high energies, and then the flow there will be conjugate to the geodesic flow of negative curvature, and therefore it will have no close contractible orbits, and therefore the Rabinowitz flow homology will just be essentially the homology of the hypersurface, which is non-zero. And since everything is invariant under deformations, you can now free yourself from that background Riemannian metric and take just any metric. Yeah? Okay, that is already giving something that was not known. So this is already showing that anything above here is non-displaceable. In particular, even in this exact case, it's telling you that the gap is non-displaceable, something that we didn't know before. I mean, we knew that the gap, that anything above the Magnier strict critical value was not displaceable simply by this great Gromov theorem. If you're above C0, you have a Lagrangian graph inside, and if you have a Lagrangian graph, then you cannot displace somehow. Which, by the way, the theorem proved by Awandandolo and Schwartz yesterday gives a new proof of Gromov theorem. Because if you have a Lagrangian submanifold which is homologous to a zero section, you also have a graph inside, and then your theorem is proving that you cannot, that the homology is zero, and therefore you cannot displace. Okay, but the fact that you cannot displace the gap seems to be new, and remember the whole gap is here, yeah? Okay, now this is to sort of convince you that the virtually contact thing is a worthwhile thing to look at, yeah? So we proved with Will Mary sort of recently that if you begin with a strictly cotepinch negatively curved manifold, and you take a monopole, sigma different from zero, then if you go to high energies, that thing will not be stable. Yeah? The reasons behind that are sort of similar to the reasons that I hinted before about the smoothness of the stable and unstable foliations for anosal flows, basically. Yeah? So for high energies, the flow is not geodesical, but it is virtually contact, and one can still define, so it's not even it's not stable, but you can still define Rabinowitz flow homology by using the uniform bands on the universal covering. Yeah, so this is the reason why the virtually contact condition is a useful thing. Okay, what do we know about closed orbits? Well, everything you could probably wish for. So if you take any value k bigger than c, then every non-trivial homotopy class will have a closed orbit with energy k. So this was proved recently by Will Mary. Actually, Gonzalo hinted yesterday how to prove it in the exact case. Basically, you can do something similar in the non-exact case. Okay, now what else do we know? Well, Chilibach, Frauenfelder, and Wancha actually computed this Rabinowitz flow homology for geodesic flows, so no magnetic field, and they actually show that it's non-zero. Yeah? So we saw that yesterday in the lecture yesterday. It's actually beautifully related with the homology of the loop space by this long exact sequence that they have constructed in the paper. And well, this was explained to us. There's now a sort of very beautiful way of looking at this with this short exact sequence giving rise to the long exact sequence, and showing also that the Rabinowitz flow homology is different from zero, also in the exact case above the strict Magnier critical values was explained yesterday. It's a beautiful result. And there is ongoing work of Mary that hopefully will show that the same is actually true when you put the twist in the non-exact case, and not just above C0, but just above the critical value of the universal covering. Yeah? So if all this works, then we will have really sort of beautiful picture for the supercritical energies, in which you get non-zero Rabinowitz flow homology related to the homology of the loop space by this nice long exact sequence, and non-displaceability for energies above the Mañé critical value and existence of closed orbits. So this is really beautiful, I think. If this gets completed, quite nice. Okay, now at the Mañé critical value, that's already there's a tough nut to crack there. So if you want to show that something is non-stable, at the moment we have criterion showing that various Mañé's critical values are non-stable, and the criterions are sort of very useful in the examples, but no sort of general theorem. But here is one. So here is one that is sort of very useful in the examples. So if you happen that at exactly the Mañé critical value you don't have a closed contractible orbit, but you can displace anything below, then it cannot be stable. This is kind of more or less obvious, right, from everything that I've said up to now, because if it is stable, then you have this thickening, and then if you can displace by length, you will have almost everywhere sort of existence of a closed contractible orbit. So then you will have a closed contractible orbit exactly at the Mañé critical value. Yeah? And this happens very often in the example. So as you approach the Mañé critical value, the closed orbits tend to disappear, to go away from either the closed contractible orbits or even some homotopic classes start losing sort of existence of closed orbits. Yeah? So this is usually a way of showing that it's not stable. Yeah? But I mean, it's kind of remarkable that we can actually prove it in general. It should be true in general. I mean, this is all the evidence of this, robust phase transition there. Once, we should be able to have a proof that it's non-stable. So this, I think, is a sort of quite a nice problem. Okay, so this is what I just said, and probably one can improve that using Gonzalo's result that we mentioned yesterday, and sort of enhance that. If you just have some homotopic class without a closed orbit, then it should be possible to prove that it's non-stable. Okay, now what do we know about contractible closed orbits? What we know is actually rather good. Is even in the monopole case, we now know that almost everywhere you always have a closed contractible orbit, yeah? Even in the monopole case. So actually Gonzalo hinted yesterday how to prove it in the exact case. His proof has to be sort of somewhat modified, especially in the case in which you have an unbounded primitive. So if you have an unbounded primitive, you basically lose all the nice control that he had in his estimates, but it's possible to sort of prove it in that case. So for the case of a bounded primitive, this result was known before, and it had appeared in Osuna's PhD thesis. Okay, and let me just sort of quickly finish, just before I go to the last example, which I'll try to answer Victor's question, an example of time. But so I'll give you a sort of brief outline of what we actually know. So I've been sort of focusing really on trying to cover the full thing, the full gap here, yeah? So trying to sort of, in this sort of last few minutes. Now, if you are actually prepared to go to really low energy levels, but without knowing how low you have to go, then there are actually better results. So, because if you really go to very low energy levels, then there are results of Polterovich, Lodenbach, and Sikora saying that you can actually displace. So you will get almost everywhere existence automatically by Schlenk's results. And if you assume sigma symplectic, you can actually say something rather very good. So this was proved by Ginsburg and Gurel. I think Victor talked about this, exactly this 2 years ago. You can actually show that every energy level has a closed contractible orbit if you are prepared to go low enough, yeah, in the energy level. Okay, now we also have, and this is really nice because we have a large collection of really very nice examples that kind of illustrate all these paradigms, all this sort of picture. So I can tell you, for example, briefly for the case of PSL2R that I mentioned before, when you mod out by the action of a lattice, the picture is really quite beautiful. So I'm going to just draw it here again. So you get this sort of this cap of size 1/4. So here, this is unstable. this is unstable. So the gap here is virtually is not stable. So everything from here down is not stable, is not contact. But the things in between are actually stable and tame. And everything here is of contact type, actually restricted contact type. Yeah, so this is the C naught. The magnetic field is the connection one form associated with the area form on a hyperbolic surface, if you like to think in those terms. So the Hollow cycle example is the symplectic reduction of this. One exact and non-homogeneous? No. I don't have an example of that. Right, so I'll just finish another one, since I have it here in the transparency and I have 4 minutes left. And so the other one, that one has a sort of similar thing, but without a gap, because we have something amenable. Yes, the other thing that I didn't mention is that, which is actually important, is that here you can always, so here you can, so this is C, yeah? And below here you can displace, this is the other thing. So you can displace, you have Rabinowitz flow homology defined. It's basically, okay, so another sort of similar thing to this, if you like. You take a sort of Heisenberg group. So this is, yeah, this, the usual Heisenberg three-dimensional group. And again, with a left invariant one form, which is written there, this Z minus XDY. And again, you mod out by a co-compact lattice. And everything descends to the underlying manifold. And then you take a left invariant Hamiltonian. So I didn't mention what the I didn't write down what the Hamiltonian was here, but there's a sort of canonical left invariant metric there for the case of the of an in-manifold, that you can write down the Hamiltonian there quite explicitly. And in that case, everything you could wish for actually holds. So here this is a sort of example with no gap, a sort of exact example in which the two critical values are the same. Everything above is contact, anything below is actually not contact, but it is stable and tame. Yeah? So we get this nice period action inequality. And displaceable. You can actually displace, so you get Rabinowitz flow homology equal to 0. So these are the cases in which you can sort of clearly see how this Magnier critical value is being, if you like, sort of detected by having Rabinowitz flow homology different from 0, going from different from 0 to Rabinowitz homology equal to 0. So and this gives, I guess, the first example showing that the space of connected components of that you could have more than one connected component for the stable hypersurfaces. Yeah. So the hypersurfaces above the Magnier critical value and below cannot be connected by a homotopy. I mean, not just going through the usual energy level, but an arbitrary homotopy. Yeah. So we have two connected components. I haven't checked that, but I think, I would guess that we have here 3 connected components because of the gap. But we haven't actually proved that.
When you go from key to L, does it change?
If you go from where, sorry?
From key to L, from one level to another, does the Rabinowitz flow homology change?
Well, it only changes if you go through 1/2.
Yeah.
Yes, it goes from that's exactly the same picture as here. It goes from 0 to non-zero. That's, if you like, the sort of final message of the talk. So somehow, if you like the way I like to think about this Magnier critical value is the value for which the Rabinowitz flow homology goes from 0 to non-zero. This is really what's going on. Yeah? So this is okay. Thank you.
there